Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will introduce cryptography. So that is the mathematics of taking a plain text message like everywhere and encrypting it. When we encrypt it, we turn it into ciphertext, which is something like this, which is gibberish. We take a secret message and turn it into gibberish so that anyone who intercepts the message can't decipher it. So the act of going from ciphertext back to plain text is called decryption. That's where we turn the gibberish back into a coherent message. So what we want is that this ciphertext can only be decrypted by the intended recipient. So these days, most cryptography is done by computers. So we use mathematics, in particular mathematical functions, for both encryption and decryption. Decryption usually involves some sort of secret key only known to the intended recipient, so only they can decrypt it. Now, in cryptography, there's always a trade-off between security and feasibility. We need to make encryption fast, and we need to make decryption fast, but only for the intended recipient. See, the thing is, I could easily turn this into some random text. I could just randomly replace these letters with characters. But if there's no sort of pattern to it, how is the person going to decrypt it? So that's what we're going to be looking at in this topic. So modern cryptography usually uses these one-way functions. So basically a function that is easy for a computer to implement, but very hard to undo. As we'll see later, one such example is it's easy for a computer to multiply two large numbers, but very hard for it to factorize the result. So when we talk about a function, we're basically talking about a mathematical machine. We input something into that mathematical machine and it produces an output. Because we're using mathematics and functions work on numbers, usually our first step in encrypting is to convert our plain text into numbers. So there are a few ways to do it. The simplest way is we make all the A's into 0, B is 1, C is 2, and all the way to Z, which is 25. We put those numbers into the function. Now, when we want to decrypt, we have our output here. We want to put it like through the function, but the opposite way. We want to reverse what's been done to the output, kind of like how we solve equations. So usually, in order to go this way, there'll be some sort of lock and a key will be needed to undo it. So let's look at one method of encryption. So this method is called the Caesar cipher, presumably because it was used by Julius Caesar all those millennia ago. So all you do in this one is you shift each letter up or down by the same number. So you might shift each letter up 4 or each letter down 3 or whatever. This is not secure. You would not get away with that in 2026. There's only 25 possibilities for the cipher. You can shift the letters up 1 or up 2, up 3, all the way up to 25 spots. So not only can we program computers to be able to decrypt this in seconds, but we can also use frequency analysis. So ETA are the most commonly used letters in English. So if I had text like this and I know that a Caesar cipher is being used, I could make some guesses. Clearly in this word, A is the most common letter. So we might first guess that E has been mapped to A. So if I put these in numbers, E is 04 because it's the 5th letter of the alphabet, A is 00 because it's the 1st letter of the alphabet. So that's what I did to encrypt. So to decrypt, I'm simply going to do the opposite. To go from A back to E, what I need to do is basically add 4. So to encrypt, I subtracted 4 from each value to get the ciphertext. When I decrypt, I do the opposite. I'm going to add 4 to the ciphertext in order to get the plain text. So let's go ahead and add 4 to each of these numbers. So there is a table in the notes that tells you which number is associated with which character, but we've already figured out that 04 corresponds to E. So 21 corresponds to V. Again, you can just get these from the table in the notes, or you can look up on Google. You could probably even write it out yourself. So we get the message everywhere. That's how I encrypted the message on the first slide. So we have a coherent message, so we know we're on the right track. If this word didn't have E as its most common letter, we might then try mapping A to T. So we could try any number of that. Again, there's only 25 possibilities. We're just looking at the most likely possibilities first. So this principle that says a crypto system should be secure if the algorithm is known but a key is unknown, it was posited about a century or so ago, but is so much more relevant today. See, because we use computers to do cryptography, we need to know the algorithm for a certain method of encryption. Sometimes the encryption is actually done on your computer when you log into a server. So we need to know the algorithm, but the one thing we keep secret is the key. That's what makes the crypto system viable. So again, most of the time we know the algorithm, but not knowing the key means that someone who intercepts the message can't decipher it. So we're going to look at a few types of cryptography in this topic. Symmetric cryptography has the key kept secret. There's only one key. Same for encryption and decryption. We're also going to look at public key cryptography, which is essentially has two keys. One's a public key that everyone can find. It helps you with the algorithm, but then there's a private key that is kept secret. We're also going to look at something like hashing. Now, hashing's a bit different because we do encrypt data with hashing, but we don't decrypt it. We just turn it into gibberish that can't be used to retrieve the plain text, the original message. And that's used when you want to store data like passwords. So on the system, a computer would store passwords as what's called a hash, as a long string of gibberish, but if someone intercepted that gibberish, there's actually no way to decipher it. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.